This is section 523. We're going to take a look at a couple of polynomial theorems. So we're going to discuss what we call the remainder theorem, and we're going to discuss the factor theorem. So let's look at the first theorem, the remainder theorem. Now, we've talked about being able to divide, and we've practiced how to divide. We have polynomial long division, we have polynomial synthetic division, and for what we're going to start doing is we're going to kind of look at ways to describe a polynomial, and a couple of these theorems are actually going to enable us to do some cool things with the polynomial. So the first theorem is the remainder theorem. Now it states, suppose you have a polynomial p of a degree at least 1 and c is a real number. When your polynomial is divided by a factor of x minus c, the remainder is the same as if you just took that c value and plugged it in. Now this is what I mean. So let's look at it in a problem here. If I were to divide this, okay, so if I were to use synthetic division real quick, 1, 7, 12, add straight down, multiply, add, multiply, add, well, my remainder is 0. That's the same as if I just took negative 4 and plugged it into the problem. It's the same thing. Now, why is this important? This tells us that dividing can find us our zeros, right? There's a relationship between dividing as a linear factor and being able to evaluate and find our zeros, which then leads us to the next theorem. So we need to know this one. That leads us to the next theorem, which is the factor theorem, that says suppose p is a non-zero polynomial, the real number c is a zero of that polynomial, if and only if x minus c is a factor of it. So this implies that we can write the 0 as a factor. So if I know what the 0 is c, I can write it as a factor as x minus c. I can state a 0 from a factor, so if I have x minus c, I could say that my factor is c, and I can use a 0 to divide the polynomial written in that form of x minus c. So I can use zeros to be able to do it. So looking at this first one, find p of negative 2 using the remainder theorem. Okay, well, that just means I could use polynomial division, because it might be a little bit easier. Add straight down, multiply, add, multiply, add, multiply, add. So p of negative 2 equals negative 3. Kind of a little quicker than just plugging it in, entering it in your calculator. You can, but I'm just saying that it's a little quicker that way. Now it says use the fact that x equals 1 is a 0 to factor the polynomial. Okay, so that means if I know that 1 is a 0, right, the factor is x minus 1, that means I can plug in 1, 2, 0, negative 5, 3, and I can go through and divide it. Add straight down, multiply, add, multiply, add, multiply, add. See? Bam, I got a 0. Now let's interpret it. Remainder, constant, x squared. So I have 2x squared plus 2x minus 3, and I still have that x minus 1, right? That didn't disappear. I factored it. I used division to factor it, and so I still need that x minus 1. Well, I can still factor this further. Okay, so a times c, right? Negative 6, factors of negative 6 that are going to add to 2. Well, 1 and 6, 2 and 3. None of them do it, so this is as factored as it's going to be. So to discuss a few connections between zeros, factors, and the graphs of the polynomial. So suppose our polynomial is, the degree is greater than 1. The following statements are equivalent. So the real number c is a 0 of p. Okay, so remember we're defining z as zeros, right? So we're saying that real number c, the 0, is going to be a 0 of p. Therefore, if you plug c in, you're going to get 0 because it's a 0. We would say that x equals c is a solution because it makes our polynomial 0, meaning if you were to solve for x, you're going to get 0. Right? If you were to set it equal to 0 and solve for x, it being a solution is the reason what's going to give you 0. And then you can, if you know what your c is, you can write it as a factor of that polynomial when you go to divide. And zeros and x-intercepts are synonymous with each other, interchangeable with each other. Yay! So let's look at this one. You are given a polynomial and one of its zeros. Find the rest of the zeros and factor the polynomial. So if I know that that's a 0, I can put that in the box, right? This is going to be x minus 1, right? X minus c, or x minus your 0. And I can write out 3, 2, 1, nothing. Okay, there's no placeholders necessary. Add straight down, multiply, add straight down, multiply, add straight down, multiply, add straight down. So rewriting what I have x minus 1 times x squared minus 5x plus 6. A times c, 6, factors of 6 that add to negative 5. So this will factor into x minus 2 and x minus 3. So let's parse what this problem is asking. It says find the rest of the zeros. Okay, so all of my zeros are going to be 1. That was given to me. Set that equal to 0, I get 2. Set that equal to 0, I get 3. And then it says, and factor the polynomial. So there's my factored form. There are my zeros. Look at this next one. Now you're thinking, ooh, fractions. Whenever you get a fraction and you have to use synthetic division, it works itself out. So 2/3 in the box. I have 3, 4, negative 1, negative 2. Add straight down. Now multiply. Well, 3 times 2/3. That cancels out, so I'm left with 2. Add straight down. Now multiply. 2/3 times 6. Well, the 3 and the 6 cancel out, so I get 4. Add straight down. Multiply. 2/3 times 3. The 3's cancel out, and I get 2. Add straight down. See? Told you. It works itself out, which is really nice. So now I get remainder, constant, x squared. So I have x minus 2/3. And then the rest is going to be 3x squared plus 6x plus 3. There's a 3 in common, so I'm going to factor out that 3. A times c is 1. Factors of 1 that add to 2 is 1 and 1. Now, see this 3 and this 1/3? Whenever you divide by a fraction, you could actually multiply that number through, so you no longer have a fraction. It'll always happen that way. So now, just writing this condensed. So there's my polynomial, and then my factors, or my other zero, or my zeros, are 2/3, and set that equal to 0, you get negative 1. Now working backwards, create a polynomial with this desired characteristics. Okay, well, it says my zeros are these values. Okay, so x minus my 0, x minus negative 2, x minus positive 1, x minus negative 1. Okay, so there are my zeros. Now if I multiply this, x times x times x times x, that gives me x to the 4th. Well, my leading term has to be 117 x to the 4th. So I put 117 in front. What did we learn today? We talked about the remainder theorem, how plugging in a value and evaluating whatever the value you get after you evaluate is going to be the same thing as remainder when you divide. And we talked about the factor theorem, which basically states that if you divide by a factor of x minus c and your remainder is 0, then we know that it is a factor of the polynomial. This does conclude our lesson. If you have any other questions, please leave them in the comments.